All right, in the last part of Chapter 6 review here, we're going to look at sections 4 through 9. We're going to talk about electron configurations and waves or light as a wave. So we're going to think of electrons. We start off with light. We talked about light as a particle. We talked about light as a wave. Now we're going to talk about kind of not light, but electrons, because they're kind of the same kind of deal. So we're going to think of electrons as a wave with mass and velocity. So they call these de Broglie's matter waves because de Broglie was the guy who did a lot of work with this. If you take another advanced chemistry class, you'll learn more about some equations and some math that go along with figuring out the momentum behind these electrons that have with these waves. But for right now, we're just not going to deal with that. So we talk about these electrons having a mass and having a certain velocity. Well, the uncertainty principle comes into play because it is impossible to know both the position and the space of an electron at the same time. We talked about this last year. You can't know how fast the electron is going and exactly where it's at, because in order to tell exactly where it's at, you have to hit it with something, and usually you hit it with a photon. If I hit it with a photon, now I saw it hit it here. Well, now I know where the electron was when it hit the photon, but now I have no idea how fast it was going because it was stopped when it was there. So I last year talked about fan blades. You can't see if the individual fan blades when they're moving. If I stop one, now I know exactly where it's at, but I have no idea how fast it's going. So you can't know both the position and the velocity or the of a electron at the same time. Okay, now we have electron density. We're talking about quantum mechanics and orbitals. We're going to go from Bohr's model with orbits and the set paths that electrons are on to quantum mechanics and the quantum theory and atomic orbitals. Well, the first thing we talk about is electron density. And this is a picture of the probability of where in space surrounding the nucleus your electron is likely to be found. And the more dots you have, the more likely it's to be found there. The less dots you have, the less likely it's to be found there. And that's kind of how they got these weird shapes of the S, P, Ds, and Fs that we're going to look at here in just a second. Based on kind of they hit these electrons with photons and kind of saw where they hit, and then you could find all these spots, and they did that a whole bunch of times, and they got these different kind of density graphs or density pictures. So they have them for the S, the P, the D, and the F, but we're just looking at an S here because that is actually the S shape. All right, they are less likely to be around the outside. They are more likely to be in the center, and we notice that from the concentration of dots that we have. All right, so we're going to look a little more closely at these four quantum numbers that we really didn't deal a whole lot with last year other than telling you what the names of them are. Okay, what you look at now is actually with all these letters you have. So you have like the S, P, D, F. You have like, 2S or 2P or 3S or whatever. And remember, like if I have a 2P, for example, 2P means that you have three different ways that's oriented, right? You have what we call a 2PX, 2PY, and 2PZ. These are where you have, remember my lobes, little dumbbells, one going this way, one going that way, and one pointing forward. Okay, one on the X, Y, and Z axis. All right, so we learned this last year. All it is that these particular things have a letter associated with them, and they actually, excuse me, these particular things have a letter associated with them. They also have a number associated with that letter because, that's not confusing. But it is what it is, okay? So, for example, right, if I have this 2P, okay, that we're looking at right here, okay, and it says that your N is the energy level. So the 2, that is N. How far away it is, 2, 3, 4, 5, 6, 7, okay, or 1, all right? The shape, okay, is either S, P, D, or F. Well, since my shape is a P, the L value, okay, so N equals 2, the L value is 1, okay? Because the shape is a P, S is 0, P is 1. I always think S's look like, zeros, they're spheres, so that's why I know I always start with 0. Okay, L equals 1, and then you have M sub L, which is based on your shape, and that's really just your number of orientations, okay, which means how many ways it's pointed. We talked about that last year where the S's have one where they're oriented, P's have 3, D's have 5, F's have 7, and so forth. Okay, they're odd numbers like that. Well, how it goes from negative L to L. So M sub L, all right, is -1, 0, and 1. Well, you notice you've got 3 of those. Because my L is 1, so I go -1, 0, 1. That gives me 3. And those 3 correspond with the fact that I have 3 different orientations. 1 is a -1, 1 has a 0, 1 is 1. So there are 3 M sub L numbers. Okay? M sub S is the easy one because that's just talking about the spin of the electron, whether it's a spin up or whether it's a spin down. 1 is positive a half, 1's negative a half. Which one is which, it doesn't really matter. So if you're trying to find a particular electron, they're only going to have one of these numbers. So say you have, okay, I have my 2p here. I'm looking for this one particular electron, okay? So I've got 3 electrons in there. I want to know what this one particular electron's quantum numbers are. Okay, so for this one electron, its quantum numbers are n equals 2, L equals 1, and M sub L equals -1. Plus, it's up, so it'll be M sub S equals, I say a positive a half. Well, it doesn't matter when you do just one of them. Okay? If you were talking about, say I had all of these full, okay, I did 1, 2, 3, and I came back here, all right? If I got rid of this M sub S right here, then this would be describing 2 electrons, because both of them have n equals 2, both of them are in L equals 1, and both of them are in M sub L equals -1. All right. If you're going to talk about, say I didn't get specific and I didn't do this one, I'm just talking about these 2, then I'm talking about 6 electrons possibly, because I have a shape of P, because the L equals 1 here, and I also have a second energy level. So I know I'm talking about the entire 2p level. So the more quantum numbers you have, the more specific it gets. If you have all 4 quantum numbers, you're talking about 1 electron. If you just be talking about the n equals 2, then I'd be looking at, 2s and 2p. Okay, and then I can be talking about 8 electrons because I can fit 2 in the 2s, and I can fit 6 in the 2p. So if I just look at n equals 2 stands for actually just 8 electrons. And then you narrow it down, pick, okay, which one of these 8 electrons is it? Which L shape is it? Is it L equals 0 or L equals 1? Okay, and then you say, all right, well, I'm looking at L equals 1. All right, now which M sub L are you dealing with? Are you dealing with all of the 2p's? Okay, so you're just using it to narrow it down. All right, and there's a big chart there on the next page of your notes where it's talking about possible values of M sub L. So notice that for you have, like say, a D shape. Okay, D, the L for D, all right, is 2. So my M sub L's should go from -2 to 2. So -2, L equals 2. Okay, so let me write that better. My L equals 2. Your M sub L equals -2, -1, 0, 1, 2. And you've got 1, 2, 3, 4, 5. 5 lines. And D's, we know, have 5 lines. Okay? So that's how you have numbers associated with like these things that we looked at last year. All right, and the representation of orbitals, we have the S, P, D, and F. S is going to be 1 orientation. Just again, you're showing the different sizes here. 1s, 2s is larger than 1s, 3s is larger than 2s and 1s. So the further away you get from the nucleus, the higher your N number is, or my energy level number. Here are my P's, X, Y, and Z. This is kind of that, again, that electron density picture where we have kind of like above and below, all right? And then I have the D's, which are kind of crazy looking things, and then we've got F's. And there are 7 orientations for F that we're not even going to get into what they look like. Okay, you have this chart in your notes, all right? And we'll look a little more at this in class together. It's a little bit easier to see. But if we have, say, this 2p here, so I have that 2p, okay? And when we look at this 2p orbital, okay? I see that right there. Okay, I've got values of -1, 0, and 1. That's my M sub L. Because my L value is 1, because it's a 2p, p's are 1. Okay, so -1, 0, and 1 for the 3 for X, Y, and Z. I have 3 orbitals. Okay, I have the px, the py, and the pz. And I also, in the 2 shell, have an s. So that's why it says 4 there, because there is a 2s and the 3 2p's for a total of 4. We'll get more into these a little bit later as it kind of goes on, all right? Because that is something kind of new. Okay, we talk about many electron atoms. We talk about electron spin in the Pauli exclusion principle. We did this last year. No two electrons in an atom can have the same spin. You can't have two up arrows. You gotta have an up and a down arrow, and we talk about these, okay? For an electron configuration, for Hund's rule, you have to have one electron in each before 2 in 1. So I have to have an up arrow in one 2p and another up arrow in the other before you have a down. You would not have a down there, okay? We have our standard notation, okay, which is either an orbital diagram or kind of the electron configuration standard notation. Okay, I've got the diagram or I've got the written out, and these should be familiar from last year. Okay, and then I've got my noble gas notation, which is dealing with a noble gas in brackets standing for a whole long slew of 1s2, 2s2, 2p. Remember, that's saving you some time from having to write out all of the 1s each time. And then whatever is left over. Okay, this here is representing my core electrons. Those are the electrons in the center. And this out here, those are my valence electrons. So I have 2 valence electrons. Okay, and this is where it comes to be important with them with ions and bonding. All right, so I have 2 valence electrons and then however many electrons xenon is for my core electrons. Remember that transition metals, okay, the D level is 1 number lower than normal. I go from a 4s then to a 3d. And it is easier to remember that order, and that's the off-ball principle or off-ball diagram where you know what order things go in. Well, it's easy to not memorize the order, but actually look on your periodic table. And that's the next part you got on the bottom of the page. Know just where the things are, okay? My S block is the first 2 groups here. Mine are blue, then you've got the D block in the middle, and you got the P block on the right, and the F's are there on the bottom, okay? Remember, it just goes in order. Read it like a map. Okay, just got to remember that 4s and then 3d when I go across. Okay, so if I would have the element there, that would end in a 4p1. If I want to do noble gas notation, I would put whatever that noble gas is right there in brackets, and then I would go 4s2, 3d all through all of them. It should be 10, and then 4p1. All right. Lastly, okay, there are a couple that I want to point out that are actual exceptions. There are more than a couple exceptions, but these are the main ones. If you look at chromium here, it says 3d5 4s1, and if you look at copper, it's 3d10 4s1. That has to do with half full levels and almost full levels, okay, or full shells. Chromium should actually be 3d4 4s2, but what happens is it's more stable to have a half full because half of 10 with the D's is 5, so it's more stable to have a 3d5 than it is to have a 3d4, okay, with the 4s1. So one of the S's moves up to the 3d and we have a half full level that's more stable. Because 4s's and 3d's are very, very similar in energy levels. They kind of overlap a little bit actually. And then as you move down, you see how they get more and more complicated. If you end up in the lanthanide or actinide series, that's when you're going to have a couple of different things. You're going to have an F and an S, which kind of seems bizarre. All right. And then if you go back up into the D block, you'll have F's, D's, and S's. Okay, so the further you go on the table, the kind of more complicated they actually get as to what you have. But you should notice that the F block is 2 lower than the row, just like the D is 1 lower. 1 number lower than the row it is in.